Okay, so in this video we're going to take a look at parallel circuits, one in which we have more than one path, which is essentially what's different between this and the series circuits, where there was only one path and only one current, but you saw that we did have to work out the rules for voltages and resistance. So in this one we're going to look at a circuit in which there is more than one path. One comment just real quickly before we start looking at the details. The word parallel doesn't have the same meaning that it means in your math class. You know, obviously that means two lines with the same slope, or two lines that don't cross, or it has nothing to do with that at all. Okay, and I know that's even more confusing because I drew the circuit to show that there were actually these parallel resistors, but they're not parallel because they're lined up like this. They're parallel because there is more than one path. And that is simply what the word parallel means. So let's talk a little bit about what happens when we have a battery which is able to supply energy. That's going to supply our voltage. And remember, the voltage is the amount of energy per charge that is going to be distributed to the circuit. So it tells you how much each coulomb of charge will receive in energy as it passes through the battery and then have available to it to deliver to the various resistors throughout the circuit. So let's follow the path. The current, conventional current, leaves through the positive end of the battery, and it travels around the circuit. And obviously at this point, nothing has really happened to it because we have not yet hit a branch. But as soon as we hit one of these first branches, then we have an issue to deal with. And that is that the current is not going to be the same everywhere now, because some portion of that current will continue on, while some of that current will be directed towards that first resistor. Okay, so this guy will go down this way, and we'll see what happens when we get down at this point. But let's look at what happens when we have the next junction. Same thing's going to happen. We're going to have some portion of the current's going to go this way, while meanwhile some portion of the current goes this way. Now, once you choose to go down this path, then obviously you have no choice. You must go down that path. And let's just follow this circuit as we go down the third path. Let's just see what happens as we return to where the junctions come back together. So these junctions are really important because they identify a place where the current could split and go in two different paths. And they do not necessarily have to be the same amount of current. So more current can go down one path or the other. But once the current comes down this way, then it's going to travel like this, where these two will rejoin to continue on in this direction. So the current from resistor 3 and the current from resistor 2 will rejoin back together as they move on through the next portion of the circuit. When they reach the last of the intersections, then current 1 plus the current from 2 and 3 will come back together to be the full current that left the battery, and now that guy will get recharged by the battery and they will be sent out. And they can take a different path, obviously, when they make their second route around. But one of the things that's really important to understand about the parallel circuits is that there is, in this particular example, there is only one resistor that you get to go through on each pass through the circuit. So remember, the idea of a circuit is a closed loop in which you can return back to the same point. But if you follow this loop, you'll see that you can leave the battery and you can go down through the first resistor. But once you go through that first resistor, you can't go through the other two. You must return. You are going to deliver all of your energy. If you are those charges that went down this path, you will deliver all of your energy, and then you will return back to be re-energized by the battery. Now, why does that have to be true? Why does the voltage here have to be the same as the voltage in the battery? Because it would violate conservation of energy, just like it would have in the series circuits. So if this battery increases the voltage on those charges by, let's say, to 12 volts, well then, as it goes around through the circuit, it has 12 volts to dispense. Where is it going to deliver that energy? Well, there's only one resistor to deliver it to. So if he raised the voltage by 12, then he must have lowered the voltage by 12. So this raises it by 12, we're at 12 volts, we come in, we drop it, now we're down to 0 volts, we head back over to the battery, we get re-energized by the battery. And that's going to be true for any of these other circuits. I mean, look, if you go through the battery and then you don't go down the first path, but you decide I'll go down the second path, but once you go through the second path, you can no longer go through any of the other paths, and you must return back to the battery before being re-energized. So one really simple rule that we can see is that the voltages are all equal to each other. And I only have 3 resistors in this particular circuit, but this would apply to any number of resistors. So 4, 5, 10, 12, a million resistors. Doesn't make any difference. we would still find that for each of those resistors that was in parallel with the battery, and this is an important aspect of understanding how to work with these circuits, is we have to have the right language. So the way I would describe this is I would say that resistor 1 is in parallel with the battery. It is also in parallel with the other resistors. Now that's different than if I put them all into one big line and then I say they are in series with each other. I say that the resistor is in series with the battery. But in this case, the right language to use is to say that each of the resistors is in parallel with each of the others because they are in different paths, and they are all in parallel with the battery. Okay, so as we said, we're going to use two simple physical principles to essentially explain why the rules must be the rules that they are. So there is an aspect of this that is problem solving and simplifying circuits and trying to work out what's the current and the voltage here. But there's another aspect of it that is just purely conceptual and requires you to essentially understand what is the logic or the justification, what physical principles are underlying why these rules turn out to be the way that they are. And in this one, I would say that this is due to conservation of energy. And that's always going to be true. It's always going to be conservation of energy when we talk about the voltages. And the reason is because the voltages are telling you how much energy the charges have. It is inherently a property which contains information about energy. So of course, anything that applies to the law of conservation of energy would apply to this also. And this is why the voltages must be the same in each of the resistors. Okay, so moving on to the next step then is time to start thinking about the current. So one thing that we know is that there will be different currents in each of these paths because only a portion of the current can travel through this resistor, and what doesn't travel through here must go through the other two. So these guys are going to separate, and this is kind of a tricky circuit if you, just the way it's drawn, could be a little bit tricky because there are actually some parts like this path right here where there's a combination of currents, and same thing over here. So if you imagine, what essentially has to happen is that this current leaves the source current, so this is IS. That source current leaves, and then it's going to break up into three different parts, and then the three different parts are going to come back together. So obviously these three parts must add up because otherwise we would be violating conservation of charge. That is to say that if there was, let's say, 10 amps left here, but only 4, 3, and let's say 2 amps go through here, so 4 and 3 is 7, plus 2 more is 9. So that means that 10 amps came out, but only 9 amps is accounted for in any other part of the circuit. Where did that extra amp go? What happened to it? It's impossible. It could not have left. There's no mechanism for it to leave. So one basic rule, according to the law of conservation of charge, is that the currents in the individual paths must add up to each other, regardless of however many that there are. Now, one little clarifying thing, this is actually kind of important. That only is true if there's one resistor in that circuit, or in that path. So if there were 2 resistors in here, then that would be a little more complicated. We'd have to take a step back and reduce that down to a single resistor. So what I'm saying is that if you have only a single resistor in each of the paths that you have in your parallel circuit, then the current in each of those paths will add up to be the current that left from the battery. Imagine that they were people. I send 10 people to go out and follow a path and return back. So I send out and 4 go down one path, 3 go down another path, 2 go down another path, and only 9 people return. Obviously that violates something. Somebody disappeared somehow magically, even though there's no physical principle that would explain why they would be missing any of the people or why would we be missing any charge. So these two conservation laws, these are the ones. These are the fundamental laws that really explain pretty much most everything that we see in electrical circuits is based on these two. One thing to point out before we move on to the resistance is this is exactly the opposite of what we saw yesterday, or which I should say in the previous video. So the voltages are the same everywhere, but the current has to be shared. And that was the exact opposite of yesterday. The voltages had to be shared, but the current was the same everywhere. So as you can imagine, the rule for this is going to be a little bit different. So let's take a look at what we need to know in order to figure out, well, what's the rule for resistance? How do we bring these guys down and replace them with a single resistor that would have the same effect on the battery that these three in this combination have? Well, remember that V is equal to IR. So therefore, I is equal to V over R. So what I'm going to do is I'm going to make a substitution in here for all of these I's. I'm going to rewrite this statement, but this time I'm going to replace it with V over R. So IS would be replaced by VS over REQ. And just a quick comment about this REQ. This is not a property of the battery. Okay, it's not a property of the battery. There is something called internal resistance, and we will look at it in future videos. The equivalent resistance is what could I replace all of these resistors with in a single resistor so that I would be able to make the calculation of the current that came from the battery. In order to know the current that came from the battery, I can't do it with these individual resistors. I need to put the whole thing together to reduce this down to a single resistor. This equivalent resistor will replace 1, 2, and 3 with one resistor, and the battery will never know the difference. Because realize, the battery doesn't know what's connected to it. It knows there's a wire on one end and a wire on the other end. And when it tries to push, there's some resistance. But it doesn't know what the combination of resistors are. It can't see down the wire to see what's on the other end that's causing the resistance. And so this idea of using this equivalent resistance is to simply replace this in the circuit with a single resistor that's going to allow us to go back to the simple rules that we've already learned, like V is equal to IR. So let's go ahead and replace all the individual currents. That will be V1 over R1 plus V2 over R2 plus V3 over R3. And that would include any other resistors that were also in parallel. So whatever number of resistors you have in parallel, that's what would be in here. You would just continue to add those together. Now, one thing really important to understand is that, as we just said, the voltages are all the same. So that means that we could divide by the voltage, no matter what it was, and it would disappear. And that is going to leave us with nothing but the resistances. But the rule is obviously a little bit more complicated than we saw last time, where all we needed to do was to add the resistors. Now we have this very unusual process where instead of adding the resistors and getting the total resistance, I need to add the reciprocals, but realize that's still not going to give me the answer because that's the inverse of the answer. So that means that once I do the math on the right side, I still have to do this operation, which is to flip it over. Take the reciprocal or take the inverse of that particular number, whatever you come out on this side. So let me put a box around this. This is given on the data booklet, but these two guys are not. These two rules are not given, but that rule is given in the data booklet. So that's where you can see that you do need to understand the logic behind this, and then it's easy to remember how the rules work. You can essentially just kind of create it in your own mind without having to memorize it, so long as you understand what the law of conservation of energy says, what conservation of charge says, and furthermore, what the relationship to these two guys are. This is the energy per charge and the amount of charge per second. So it makes complete sense that this has something to do with conservation of charge and this one has something to do with conservation of energy. Okay, so what we're going to do right now is let's take a moment to put a line underneath this and let's take a look at an example. And this is going to be kind of important because I want to use the same example from the previous video. And the reason is that that's going to allow us to make some comparisons to see with the exact same battery and the same resistors, you get a completely different circuit. The values and the currents and voltages are going to be completely different in the circuit compared to what they were for the series circuit. So in this case, let's make a nice large diagram. Let's just take a second to everybody make this large diagram. If you can make a pretty good sized box, maybe at least half the width of your paper, that should be enough. You can already see that I didn't put the resistor over here. Sorry about that. All right, so 3 resistors. We have the same 12-volt battery. So VS is 12 volts. And what we need is the labels for the resistors. So let me turn this sideways for just a moment. And let's do R1 is equal to 5 ohms. R2 is equal to 10 ohms. And R3 is equal to 15 ohms. Okay. All right, so in any of these circuits, this is the same premise that you're going to be basically following. This is kind of a simple problem-solving strategy for when you have complicated circuits like these. So what I'm going to do is I'm going to replace the 5, the 10, and the 15 with a single resistor that the battery will perceive as the same, because there will be no difference in terms of the way the battery sees this. So our goal is to get to this. Okay, and this is not a very complicated circuit, so it will not take us very long to get to that point. So 12 volts and Req is equal to question mark. All right, so let's take a look at how you use this resistance equation. Obviously, just for the record, I already know all the voltages, right? Because the voltages are the same as the voltage on the battery. So it's 12 volts, 12 volts, 12 volts. But the currents are not going to be equal to the current coming out of the battery. I'm going to add them together to be the current coming from the battery. So let's take a look at how this rule is going to actually play out. And I'll show you two options for dealing with the math. So first of all, it's 1 over 5 plus 1 over 10 plus 1 over 15. Oops, sorry. All right, so one way that you can handle this problem would be to find a common denominator. It's not required, you don't need to do it, but it definitely will work if you find a common denominator. Now, if you think about this one, you see things that are lots of multiples of 5, but unfortunately 10 is not a multiple of 15. So while 5 is a multiple of, or 15 is a multiple of 5, 15 is not a multiple of 10, not a whole multiple. So what I need to do is to find what is the smallest number that I could work with here that will allow me to have a common denominator, and that smallest number would be 30. Now, you technically can use any common denominator that you can find, but usually it's going to be easiest if you pick the lowest common denominator. And now realize this is not algebra that I'm doing. Okay, I'm not doing any algebra right now. It is perfectly acceptable for you to multiply the top and the bottom of a fraction because it will not change its value. So in other words, 1/2 multiplied by 3 becomes 3 over 6, but that's still 1/2. It's still the same proportion. So what did I multiply by 5 to turn it into 30? I multiplied by 6. What would I need to multiply 10 by to make 30 on the bottom? I'd have to multiply by 3. So I've got to do that on the top also. And same thing with the 15. I need to multiply by 2, and that is going to give me 11. Req is equal to 11 divided by 30. All right, so quick point. That's not the final answer. That's not the final answer. So what I need to do is to say that Req, and what I need to do is to flip that over, so that's 30 divided by 11, and that is 2.73. And then that is ohms. Now, how does that compare with the series circuit that we looked at yesterday? Well, the series circuit said just add up the resistors. So that was 30. So that is 11 times more resistance in the circuit when it was in series than it was in parallel with the exact same battery and resistors. So that is much, much lower resistance. And that's a general property of all parallel circuits, is that they're going to have lower resistance than the individual resistors. And we'll talk about that when we start doing the combination circuits. Okay, so there's a huge difference between the series circuit. 30 ohms for series, only 2.73 for parallel. As I said, I already know the voltages, so I'm just going to write the answer down. V1 is equal to V2 is equal to V3, and that is all equal to 12 volts. Done. So at this point, I have the individual resistors, I have the total resistance, and I have the individual voltages for the individual circuits. Now it's time for us to come up with some information about the current. So what I would like to do, there's several ways I could do this. There are several ways that I can do this. And actually, before we leave this, let me just point out to you that you don't need to find a common denominator. That is not a requirement. Look, it's really not that complicated. I'm going to take 1 divided by 5 plus 1 divided by 10 plus 1 divided by 15. That's equal to that. Now I'm going to put second function answer inverse. There's my 2.73. That's what I would recommend. If you can see that it's easy to find that common denominator, then sure, that's not a bad way to go. But if you don't see an obvious common denominator, and most of the time you won't, then there's no reason why you need to do that. Don't even worry about it. Just go straight to your calculator and move on. Like, that's just wasting a lot of time for a type of math that I'm not asking you to do. You can do it in your calculator, is fine. All right, so the next step then is we have now got the equivalent resistance. Let's figure out what the current is in the circuit. Remember, IS would be equal to VS over REQ. So that would be 12 divided by 2.73 and 12 divided by 2.73 is 4.4. Now, what did we get for the current yesterday when we were looking at the series circuit? Well, we got 0.4. We got 0.4. And let's just do that math. That's real simple. That is 11 times more current than I got in the previous day. In other words, 11 times 0.4 would be 4.4. So in this combination with the same circuit, or the same resistors and the same battery, I got 11 times the amount of current that I got. And why did I get 11 times more current? Because I have 1/11th of the resistance. So that should make complete sense. Of course, if the resistance is 11 times smaller, then that will translate into 11 times more current. So at this point, we have almost everything. There's really only one thing left for us to figure out, and that is, what was the individual currents that went down each of the three branches? So let's go ahead and calculate that one real quickly. Let's do, let me see how I'm going to do this. Let's do it this way. I1 would be equal to V1 over R1, and that would be equal to 12 over 5, and that is going to be 2.4. And then I2, which would be V2 over R2, that would be 12 over 10, so that would be 1.2. And then finally, I3 is equal to V3 over R3, that's equal to 12 over 15 to give me 0.8. And what is the total of this? Exactly what I got from the original calculation. I calculated them each individually. I got 2.4, 1.2, and 0.8. When I add them all together, they add up to exactly what the battery was sending out, which is important, because if it didn't do that, then that would indicate a calculation mistake, because otherwise you'd be violating a physical principle. And that's the basic premise about how you're going to do this. You're going to, I find the equivalent resistance, use that equivalent resistance to work out the current, and then once you have the current, then you can go back and start working out the little details. So you kind of work your way down to a simpler diagram like this, and then you start working your way back through the other diagram to kind of fill in the little details. And that's how you solve some parallel circuits.